Tonight we're talking about torque, which I like to think of as your ability to twist something or cause something to turn. So imagine if you've got a wrench and you're trying to use that wrench to turn a bolt, so the bolt's down here. You can apply a force on the wrench to turn the bolt, and that wrench will cause a force on the bolt. What you might have noticed, though, is depending on where you hold the wrench, if you've ever done this, depending where you hold the wrench, it can be easier or harder to turn the bolt. And in fact, if you tried to hold the wrench up here, it'd be really hard to get that bolt to turn. But if you turn it back here, or hold the wrench back at the back, it's easy to get the bolt to turn. Now, a few things to realize: when that bolt starts turning, it's going to turn in a circle, and your wrench is also going to take a circular path. So if we completed that out, hopefully we make a circle. And this is similar to the idea if you've ever been on a seesaw or teeter-totter, where you got two people sitting on a board with a fulcrum in the middle. Two people on this thing balancing each other out. You might have, if you've ever played with a seesaw, noticed that the closer you get, the harder it is to make, the closer you get to the center, the harder it is to make the other person move up or down. But the further you are from the center, the easier it is to make that person move up or down. And the reason for that is explained by torque. Now, torque is, again, like turning power. It's really the circular analog to force. So it's really hard to talk about forces in a circle because your force might be different depending on where you've, again, or your effectiveness of your force, rather, might be different based on where you've put your hand in that circle. According to the equation for torque, torque equals force times your distance from the center, your radius, wherever you're applying that force. The bigger your radius, the more turning power you have. So when I've got my hand all the way at the end of this wrench, my radius is 0.28 meters, and I have a certain turning power. Now if I put my hand halfway, my radius would be 0.14 meters, and I would have less turning power to cause this bolt to turn. And now I'm going to stop saying turning power and say torque, because you've got to get that phrase in your head. And as shown in the diagram on this bolt, we could apply a force back here on the wrench, and then that bolt, thanks to the mechanical advantage of our wrench, experiences a stronger force to turn it. And so the principle of torque is letting us know that the further back we are, the more our force will be applied at the actual object we're turning. And that's really all this equation is about. The further away you are, if you're trying to turn something in a circle, the further away you apply that force to whatever your lever is. So in this case, our wrench is acting as a lever, the thing we're going to turn with. So the further back you are on your lever, the more torque or turning power you have. Torque equals force times radius, where the radius is how far you are from the thing you're trying to turn. How far you are in the radial direction, that is, along the radius of the circle. Now we can also apply torques at an angle. So imagine if I have a door, this will be the hinge on my door, and I want to close that door. Well, I could apply a force this way and get that door to close. You know, I could probably also not push straight on the door. I could push maybe a little bit this way and get that door to close. However, you know, if I pushed on the door this way, it's not going to move. And the torque equation that counts for angles can help us understand this. I get more torque for my force if I push perpendicular to the thing I'm trying to turn. So in the example of the wrench turning the bolt, it's going to be a really crude drawing of a wrench turning a bolt. If I push perpendicular, I get more torque. If I push at an angle, I get a little less torque. And if I push parallel, I get no torque. This equation explains it. In fact, if you've got a calculator handy and can try this, sine of 90 degrees, whenever you apply perpendicular, the sine of 90 degrees is 1, and so you just have force times radius. The sine of 0 degrees, when we're applying parallel to the door, sine of 0 is 0. And so if you apply parallel, you get 0 torque. The whole equation becomes 0. And the sine decreases from 1 to 0 as you go down. So sine of 89 would be slightly less than 1, so forth and so forth. Sine of 1 would be slightly more than 0. Those are all in degrees. Big takeaways so far. The farther back you are on your lever arm, the more torque you get. And the closer to perpendicular you can be to applying your force, the more torque you get. Every time you angle it, you lose a little bit of your torque. All the way to when you're pushing straight in, you have no torque. And that should make sense. If you ever open a door, in fact, go try it with a door, and then just push straight on the door, not trying to open or close it, but just get beside the door so that you're looking at the thinnest part of it and push in on that. The door is not going to turn if you push exactly in on it. And the equation for torque explains that. We have no torque when we push parallel. So let's look at two simple uses for this equation. A person exerts a force of 55 newtons on the end of a door that's 74 centimeters wide. Now, drawing a picture with torque is going to be helpful. You may also need to draw free-body diagrams in certain situations. You might have to actually figure out what the force is that's being applied on the door. So we apply a 55 Newton force at the end of the door. I'm not going to draw it yet because I don't know if that's at an angle. I do, however, know that the door is 74 centimeters wide. What's the magnitude of the force first if the force is exerted perpendicular? Okay, so first off, we have a 55 Newton force perpendicular. It could actually be the other way on the door, maybe down here. The question is ambiguous. I'm just going to draw it like this. That is simple for me. So pushing straight down, again, could be pushing straight up. This question's unclear. I want to find the magnitude of the torque. So T, and you usually do this pretty curly for torque, T is force times radius, where the radius is how far you are. Now let's think about why that is. If this door were free to swing all the way around, it would make a big old circle. And it would make a circle such that the length of the door is the radius. So it would make a circle that extends beyond my screen, wherein the length of the door is the radius of the circle. So I can now sub in the torque. I remember, again, very curly T, so it's not confused with tension or time. 55 newtons times radius of the door, of course, in meters. And our torque is then, I get 40.7, or about 41 Newton meters for torque. Now, those of you who are good with units might think, wait, isn't a Newton meter a joule? The Newton meters are the same units for joules. However, when we're talking about torque, it's customary to just leave it Newton meters, because to say a torque is an energy is not quite right. It's how effective something is at turning an object. And so even though our units suggest that torque is an energy, that's still not an accurate description. A torque is your ability or your effectiveness to turn something in a circle. And so in order to keep that straight, to keep from confusing torque with the ideas of energy, even though energy is also ability to do something, potential energy, the lines get fuzzy. But in order to keep those ideas straight, we're going to use Newton meters in my class for the units for torque, and pretty much any physics class that you would take, Newton meters are going to be the units for torque, because it's, again, its ability to turn something in a circle, and the lines between torque and energy are fuzzy. We're not going to get into that. We're just going to say torque's ability to turn something in a circle, and that's measured in Newton meters. Now let's take a look at part B. Kind of minimize part A to give us some room. Part B says, now what if we apply the force at an angle? So let's take a look at that picture. I've got my door again, still just as wide. And this time I'm going to apply that force at an angle of 45 degrees. And it says at an angle of 45 degrees to the face of the door, so I should measure that angle from the actual door itself, 45 degrees. Although 45 is a nice angle in that it doesn't matter if you did sine or cosine with it, so even if we were to measure the 45 up here, it wouldn't matter. Anyway, torque measured from the surface of your lever arm for the angle it is. If you measure the measure the angle from the lever, force times radius, how far you are, times sine theta. Now, if you are worried about would it ever be cosine theta, you don't need to think about it that way, although you could make some arguments that there are cases where you use cosine theta. Instead, what you should do is just always try to figure out what the angle with respect to the door is. So maybe if it gave us 45 back here, we could subtract 45 from 90 and say, oh, well, this angle with respect to the door is 45 degrees. So if this is our door or our lever, we want to try as best we can to measure the angle with respect to the door. And that lets us use FR sine theta. So now torque is force, 55 newtons, radius 0.74 meters, times the sine, ran out of room there, sine of 45 degrees. And this time I get torque is about 29 newton meters. Torque gets less when you apply it at an angle. And so think about if we're applying the force perpendicular, we get our most effective turning power. At an angle, less effective, and parallel, we'd get none, because sine of 0 is 0. And that's it. Hopefully you've got torque. It's a pretty simple idea. The further you are from the center of your lever arm, whatever you're trying to turn, not the center of the lever arm, the center of the circle you're making with the thing you're turning, the more effective your turning power. And the closer you are to applying that force perpendicular, the more effective your turning power.